So thanks a lot for attending to this first webinar of Evolve. So we have 1 hour together. I'm the project coordinator from DTN, Jean-Thomas Acquaviva. And we have several speakers today. We have Nam Nguyen from ATOS. He's the managing prototyping, hardware prototyping at ATOS in Les Clays. Anthony Chazapis, who will speak about the software aspect of the project with a senior researcher of Force. And then I will conclude with some discussion about the use cases, and also will try to answer to the question. So about the question, you have 2 ways to ask the question. So now people are more or less all familiar with Zoom. Either you go through the Q&A interface and you drop your question, or you can also write them directly in the chat. We collect the question and we will ask the question at the end of all the presentation, so after the use cases presentation, and we will try to answer and to have a discussion with the audience. I would like also to mention that this webinar is the first of a series, so we have 4 more. It's always on Wednesday and always at the same time. So next Wednesday, we'll have a kind of dive in on another topic, so we'll present this later today. A few words just to speak about the project itself. So it's a H2020 ICT 11. So it's a fairly large project. It's a 14 million euro project. There is 19 partners, so all over Europe. And we are somehow reaching the end of the project. We are month 30. As most of the ICT 11 project from this batch, so almost 3 years ago, it's about convergence of HPC, big data, and cloud. So we are going today to try to provide you an overview of how did we manage this convergence. So a few years ago, let's say that back in 2000, even maybe exactly 2001, an application was seen as some kind of a monolith of logic, a black monolith of logic. But nowadays, this is no longer the case. Things has becoming much more, I would say, dynamic. So typically, an application nowadays is more a workflow. So we have several components which are orchestrated, and there is a flow of data from one component to the other. And each of these components has a very specific role in the workflow. For instance, we can have a first stage about data curation. So we can imagine that we are fetching a large amount of data, and we are going to apply some regular process, like a Gaussian filter on an image or some any kind of data curation. For this regular process, maybe FPGA will be extremely convenient. Later in the workflow, once the data has been curated, we could also employ some kind of machine learning. And here, in such a case, GPU is the right hardware platform to do so. And then still in this, I will say, imaginary workflow, we could have a stage on numerical simulation. So simulation is still a big part of HPC, and I think it's also still going to grow. On numerical simulation, we need many cores, so parallelism and floating point intensive. Then again, it's a different platform. And ultimately, we could have some kind of visualization or analytics on the data. Each of these stages has a very different requirement in terms of hardware footprint. So what is the right platform in order to deliver the best service for this workflow? So this is what we arrive, I mean, the designs that ultimately we had for Evolve. So we went to a heterogeneous platform where we have, I would say, the processing unit on the left side. So this is a yellow square. On this processing unit, they could be like traditional CPUs, but they can be also augmented with some accelerator, hardware accelerator. So the green one on the top of the picture, they are GPUs. The blue one at the bottom, they are FPGA. So this is to accelerate the processing, to take into account, I will say, the specificities of the process. But the nature also could be a bit different. So if you look at the first column of CPU on the top left, on the left of the slide, all this processing unit has been augmented with some kind of local storage. So here the idea is that we want to have a large amount of data, several terabytes, with a low latency access. So we have NVMe within the compute node. And then if we want to go further, we have to go to the network. And the data lake is not uniform, it's also heterogeneous. So we have two tiers, one with flash, low latency, high bandwidth, but small capacity. And then ultimately, we have the capacity tiers made about hard drive. So what do we have in terms of software? So the heterogeneity is not only about, the hardware part. Also, since we try to make a converged platform, we have to deal with the existing software stack. On HPC, it's something on the right, the blue stack. On big data, the pink stack on the left. Both have been built on the top of Linux, but they have been evolved and built, I will say, in completely independent way. A lot of work in Evolve has been about building bridges and connector at the right place in this figure in order to allow, for instance, big data application to run on the platform without any changing in the application itself. But then, thanks to the connector to the HPC one, we can trim down the thickness of the software stack in order to be closer to the hardware and to provide better efficiency. So when I say we've built, there is some physical results. So here there is a picture of the system which is hosted at ATOS facility in France. So there is several racks of hardware, processing unit, storage, and network fabrics. And we have also some real results, which is, I will say, fortunate at this stage of the project. So for instance, here, one of these applications that I will detail a bit further, maritime surveillance. When we start at T0 on where we are now, 30 months later, the application, the time to result has been reduced by more than 100. So it's a very large acceleration, and it's one of our success stories. We are quite happy with this one. So just a few words about the use cases. We have 3 use cases which are focused on satellite images. So I will detail them later, but here's the idea is that we have a very large amount of data on what we do with pictures. So obviously there is this idea of regular process, but also there is a lot of AI into this. And by the nature of the data that we are manipulating here, GPU are very well suited. The second set of application, it's about mobility. So we have here application either from the automotive market or from public transportation. And we have also some kind of in-between. So the BMW use case, even if BMW, of course, is an automotive manufacturer, is some kind of public transportation as well. So you know that nowadays the borders are a bit blurry. And here, just what I want to emphasize, it's not only about, different requirement in terms of technology, but what we want to show also is that the platform has a meaning, as value for different business verticals. So HPC, the convergence with HPC on cloud can accelerate results, not only for some specific field, but across a large board of application. And when I say acceleration, it's not just about the result, it's about the business itself. So it's a user-centric project. We don't want to have the user spending hours and hours understanding the platform. We want to smooth the business. So again, some results in automotive. Here, this is for predictive maintenance for engine. And what we do see is that thanks to the injection of HPC on hardware acceleration and parallelism, it's another, I would say, nice output, nice result of the project. We have increased the capabilities, and we have reduced the time to result by a factor of 50 without changing the application. It's still a big data sitting on the top of Parquet, the Apache database, and the application is able to deliver much faster results. So, of course, I'm a bit over optimistic, but I would say that at this stage, we can say with a bit of confidence that it works. So it works because we have several use cases where we showcase improvement. So we take a big application, we run it on Evolve, and it's faster, it's able to crunch more data, so it works. But also, as I mentioned before, there is a boost of productivity. So the complexity of expressing a workflow has been considerably alleviated in Evolve, thanks to I will say the software development which has been made. Everything, by the way, is open source. And now we have all the framework to express efficient workflow with a limited amount of work. So that's really the core result of the project. We still have some open challenges, but maybe I will keep this one for the discussion later. And now this is time for our next speaker. It's Nam, who is going to present the infrastructure of the project. Again, if you have questions, drop them in the chat, and we will collect them and address them at the end of this webinar. Thanks for your attention.
So, good morning, everybody. Thank you very much, Jean-Thomas, for your introduction. Do you see my screen?
Yes.
I put it in full zoom. Oh, I'm sorry, my camera is broken, so you cannot see my face, but I don't think that it is a big loss. I will now present you more details about the heterogeneous computing platform, as said previously, Jean-Thomas. And I start with brief introductions in order to talk about our motivations. So in the design of the Evolve Hybrid HPC platform, our main goal is to enable the convergence of HPC with big data and using AI methods. And by doing so, our second goal is to support and improve the performance of the different use cases in the Evolve project. Our background goals also to investigate with all those actions, development actions, to investigate the system architectural evolutions for the futures of HPCs. And more than this, we will focus on the accelerations of HPC computing and data movement by introducing hardware and software acceleration technologies with a focus on AI and methods, and to enable the evolution toward HPC, cloud, edge computing for the future. So in achieving those goals, we are well aware about the technical challenge we have to face, and particularly the convergence of HPC, big data, and AI represent one of those challenges, because these are different domains up to now. The expansions of HPC scope to the cloud also represent some technical challenge, because HPC is to now more dedicated to some kind of close exploitations on big sessions, long sessions of simulations during days, months, and years. And now we have to open it to the cloud with streaming of data from the outside world, which is something which is rather new and represent a lot of technical challenges for the HPC. The scalabilities and interoperabilities of different computing technologies represent another very big challenges in this. So I will go back to this point afterward. And in order to handle this, we have also to take into account the convergence of acceleration software attacks for those different computing technologies. And while doing all those actions, we have still to maintain the availabilities, the reliabilities, accessibilities, and security features of HPCs. So here's the introductions of our motivations on the design of the Evolve platforms. And now this slide presents an overview of the Evolve hardware clustered architectures. The backbone is an InfiniBand FDR networks, which is used to interconnect compute nodes together with I/O nodes and storage nodes. And this networks is complemented by an Internet networks for the purpose of management features. So as you can see in these architectures, already two originalities. The first one is, as I already said, Jean-Thomas in his previous presentations, the presence of bus buffers in order on the path from the compute nodes to the storage nodes in order to accelerate the movement of data. And the second point is that on the management, you can see that there is implementations of virtual machines, Dockers, and Kubernetes in order to open such an HPC platforms to the cloud. So here, the already two main originalities of such platforms. And now let's go a little bit more in details about the different components of this architecture, starting with the computing technologies. So the compute nodes of such an architecture is composed obviously with traditional CPUs, and in our case, we use the Intel CPUs of different families, from Haswell to Skylake CPUs. Why there are those different families of CPUs? Due to the fact that it is due to the fact that the platform is continuously upgraded. So not once at the same at the times, but some nodes are upgraded continuously with new CPUs when available. So there is a difference of different families of CPUs on this platform. They have they share the same kind of features, which is they are almost homogeneous multi-core CPUs, and they have different characteristics in terms of cache currents, cache size, etc. But they share the same protocols of cache currents and memory consistency. In our case, it is a UPI protocols used by Intels on those CPUs, and more specifically, the UPI version 1.0. The difference also, as I said previously, of those CPUs in terms of their frequency, in terms of the number of cores, in terms of the cache size, and the compute nodes which are composed from those CPUs are also varying in terms of size. And there is some kind of limitations in terms of interconnection between those different CPUs in order to provide a shared memories domains. But when we want to go over these limitations, we have to introduce also some node controllers, and in which case, at each compute node, we also see some kind of NUMA factors in the access to the memories of different CPUs of the same compute nodes. Some of those compute nodes are also equipped with GPUs, which once again are of different families from NVIDIA, K20, P40, and now V100. Those different GPUs are characterized by the number of streaming multiprocessor, number of cores, etc. And they are supported by different programming models from TensorFlow to MATLAB, OpenMP, OpenSCC, CUDA, etc. Some of those nodes, compute nodes, are also equipped with FPGAs, and today there are two types of FPGAs on those compute nodes: Altera Area 10s and Stratix 10s, both from Altera, that means from Intel. They have a different characteristics in terms of CLBs, logic elements, LUTs, embedded RAM, DSP, etc. They are supported by different programming models from either the hardware description language, BHDL system Verilog, or using OpenCL standard in order to express it in a software approach. They have also different kind of implementations, either discrete, that means that interconnection together with the CPUs through standard PCI Express protocols, or more integrated implementation, that means that using, as I said previously, for the CPUs, this UPI protocols in order to allow the access from those FPGAs to the memories of the CPUs in a current manner. So the challenge for those implementations of those FPGAs is how to handle multi-FPGAs in such an approach, which is, how can I say, much more challenging than for other accelerators like GPUs, for example, which already benefits from existing protocol linking those GPUs together. And more recently, in terms of computing, we also introduced in the Evolve platform new technologies of computing, which are the VPUs, as exemplified in here by the clusters of 8 MEMEX 10s from Intel. They are supported by the OpenVINO toolkit, and they are PCI Express-based accelerators. So here for the computing technologies, a little bit some information about the memory and storage of those of this platform, of this evolved platform. In order to size the memories on this platform, we use the first formula, which is obtained from the benchmarks, HPL, HPCG benchmarks for HPCs. That means that this formula suggests to use about 2 GB per x86 cores, or 1 GB per PowerPC cores. We are also aware that there is other benchmarks which suggest another kind of formulas, but according to the characteristics of the use case in Evolve, we have adopted the first formula in order to size the memories for our compute nodes. Already said before by Jean-Thomas, and in the previous slide, in terms of memory, the originalities of the platform is also the introductions of DDN's burst buffers in order to accelerate the movement of data from the compute node to the storage nodes. And in terms of capacities of storage, we have up to some hundreds of terabytes today in the Evolve HPC clusters, and there are also some local disk on some computing disk in order to support some experimentations in terms of in storage computing ongoing on this platform. For the interconnected fabric, so it's already said, there is an InfiniBand FDR networks complemented by Internet in order to interconnect in hierarchical manners in using the factory topologies, those different compute nodes together with the IO nodes and storage nodes and management nodes. So on the right side of the slide, you can see the hierarchy of the memories in conjunction with the different technologies of interconnections and computing. As the main points of this platform is to provide accelerations, computing accelerations, so I focus a little bit more on how those accelerators are implemented in the Evolve platform. So I go briefly in here that the main accelerators are GPUs from NVIDIA and Stratix 10 and Aria 10 from Naratech. And they are interconnected as illustrated on the right-hand side of the slide. They're interconnected for respectively for the GPUs to the CPUs using either the PCI Express or NVLink protocol, and for the FPGA using either UPI in the kind of integrated implementations or PCI Express to the FPGAs. And those FPGA boards are from Naratech, the 520N boards, and they can be connected together to the FPGAs using some custom protocols between those FPGA boards using the QSFP connectors, as can be seen on the figures at the bottom of the slide. So this is one of the main points, and which presents some kind of challenging when we introduce such accelerators which are FPGAs. When we go over the usage of one FPGAs, how we can handle those FPGAs together, it takes a lot of work in order to interconnect those FPGAs together using some custom protocols. How do we synchronize those FPGAs together in terms of clocking between the different FPGA boards? So here are the kind of big challenges we have to face in order to provide, as I said in my first slide, a scalable approach to the usage of those technologies. And afterward, also the problem is how to have a good interoperability between the FPGAs together with older accelerators like GPUs. This is another kind of challenge. Today, we have to go through the CPUs through the in order to communicate between them. The GPUs between the GPUs can be communicated through using some kind of NVLinks, and between FPGAs they can use, as I said, custom protocols. But between the FPGA GPUs, we have to go through the CPUs for this purpose. So it can still have a lot of potential improvements in the connection between those different accelerators technologies. And more recently, as I said in the previous slide, we have introduced the GPUs as new accelerators dedicated to the inference of artificial neural networks. It is composed of a cluster of 8 MEMEX from Intel. So this is for the hardware part. For the software part, this slide reuse a little bit what has been presented by Jean Thomas previously. So it is a stack of software, somehow classical stack of software for HPC, starting from the abstract layers for the hardware, operating system, and different schedule and file system management. And for the programming environment, there is some new introductions in order to support the different accelerators for the programming models, OpenCL, CUDA, but also other tools in order to support the different programming models for FPGA, for example. Talking about the Quarkus in order for the compilations of those devices. Afterward, we have cloud services, virtual machines, and cloud service containers. So I won't develop all those stuff because it will be done by our colleagues for afterward. And the next layers will be about the one API layers in order to support the OpenVINO software, which is here in order to accelerate in terms of software the inference of machine learning applications. And obviously, we have also implemented some standard frameworks like TensorFlow, Keras for this purpose. One of the points I would like to focus a little bit more about that, because it is one of the challenges, as I said previously, that how we can mix the different accelerations technologies together. So each accelerators are supported by its programming models. We have for the CPUs, OpenMP, MPI. For GPUs, we have CUDA, OpenCL. For the FPGAs, we have either HDL modelings, OpenCL. And so how do we mix all those stuff? And it is a big challenge in order to be able to get the expected performance from those accelerators. Let's take just a look for the pure CPUs, for example. So you have a large variety of combinations between MPI, OpenMP. You can go from the pure MPI to the MPI OpenMP with a one master process with different steps from OpenMP. So that's a very large combinations of those programming models, which should be done, selected according to a lot of different criterions, like memory management, load balancing, and the criterions of performance versus the memory occupations, memory footprint. And while taking into account the numerous factors, the message size in order to exchange between MPI, the synchronizations between those different processes. So this is only for the CPUs. The problem is already rather complex. And when you add to these problems of CPUs and new accelerators like GPUs and FPGAs, so you have to combine together with MPI, OpenMP, CUDA, OpenCL, and all the programming models related to FPGAs, for example. You can see that they, as you said, in the figures on the bottom right side of the slide. One of the possibilities of mixing all the programming models together, but you can imagine that there is a lot of different possibilities to mix all those programming models together, and it depends on a lot of the kind of criterions you want to take into account, and the kind of performance, the kind of constraints you have to take into account for the applications. And more than this, the tools provide, the different programming models provide in order to support the different acceleration technologies should also be compatible together in order to be able to provide optimal communications between those different technologies. For example, multiple CUDA aware of MPI implementation, for example, which should be allowed to have communications between directly between GPUs without going through the CPUs. So I come now to the conclusions rapidly. To recall briefly, once again, the different hardware and software technical challenges I said in my first slide. So the challenge is about the convergence of HPC, big data and AI, and the openness to the cloud, scalable approach to heterogeneous computing technologies, and the convergence of the acceleration software stacks, while respecting the availability, reliability, accessibility, and securities of HPC. They are the main challenge we have to address during the whole durations of the Evolve project. And by dealing with those challenges, in fact, we target the openness of the architectures toward the evolutions trends, which are, first of all, to support the exascale computing. Afterwards, we have to rethink the complete architectures of HPCs in order to be able to deal with this kind of new performance targets in order to solve the problems of energy consumptions in bottlenecks of data movement, etc. And also to support the co-design approach, which is much more optimal than the only traditional approach of implementing an applications on the an existing infrastructures. That means that we have to tailor the application itself, and together with the customization of the infrastructures in order to obtain the optimal results we can expect from these applications. And afterwards, obviously, how to evolve toward the HPC, cloud, and edge computing in the future, but already in the present. It is one of the main targets for all the providers of computing systems. So I have finished my presentations, and I leave the floor to Anthony from France for the next presentation.
Thank you, Nam. So can you see my screen, full screen, the slides?
Yes.
Yes, okay. So hello from me. I'm Anthony Hazapis, and I'm a research associate in Forth, Greece. I will talk briefly about the software platform in Evolve. So we have seen that the challenge of Evolve is to build a consolidated platform which supports high-performance data analytics applications running on HPC hardware. And the goal is to handle the needs of processing extreme scale data. So we combine HPC infrastructure as presented by Nam for performance, big data frameworks that provide scalability, and cloud services for their portability and ease of use. And the combined software stack is there to allow the real life use cases of Evolve, which Jean-Thomas will talk about, and several proof of concept applications that cover a wide spectrum of industrial and academic use cases. So traditionally, these types of applications fall into one of two categories. They are either implemented using specialized code like MPI, running bare metal on dedicated equipment, or use some big data framework like Spark, for example, which can scale out in VMs or containers in the cloud. Ideally, we would like to mix and match the best practices from HPC and big data computing to support both types of applications in a consolidated software stack. Early on, we decided that our best approach is to use Kubernetes as the execution environment and containerize both HPC applications and big data frameworks. Kubernetes abstracts the hardware resources, which allows us to replace and scale the hardware independently of the software stack, and it allows us to seamlessly exploit hardware-specific HPC features like the InfiniBand network or accelerators. Using containers enables us to unify both approaches, and we can run different software stacks as part of the same overall workflow, which facilitates ease of deployment, isolation between users, and portability. So applications running in the Evolve framework are not these monoliths as shown by Jan Thomas. They are complex graphs, workflows that run some containerized code as part of each node. These workflows are created, configured, and triggered from notebooks that also set the stage for execution, collect the results, and present the visualizations. It's not uncommon for an application to use a combination of different frameworks and microservices like Spark, Dask, TensorFlow, Kafka, even MPI, and others. So it's practically unlimited. From a high-level perspective, the main components of the Evolve platform are shown in the figure. At the bottom is the heterogeneous hardware infrastructure, as previously presented, which is integrated into a single execution environment using Kubernetes. In practice, we have extended Kubernetes with novel workload placement and scheduling features, as well as a new storage abstraction called the Unified Storage Layer. We have also integrated a wide selection of big data, cloud, and HPC software frameworks as microservices, including a state-of-the-art visualization service that extends to the front end. On the right, you can see a vertical monitoring layer, which collects runtime statistics from hardware and software components to assist developers into understanding the performance characteristics of their applications and to enable automated fine-tuning of container placement and scheduling. So in the following slides, we will briefly go into the specific details of each component briefly, and more details are in the upcoming webinars. The hardware platform is a scaled-down version of an HPC computing environment. It integrates numerous accelerators, as Nam has shown us, including GPUs, FPGAs, and VPUs into a cluster of processing nodes, which is a highly heterogeneous setup. This infrastructure is presented as a unified execution environment to application microservices via Kubernetes, so the industry standard container orchestration framework. In Evolve, we containerize all applications and their respective frameworks and run the resulting containers using a workflow controller. In the process, we have identified several issues working with Kubernetes and have been working on implementing novel solutions to tailor the execution environments to our needs. First, we have applied custom resource management policies. And Kubernetes uses a discrete pluggable service called the scheduler to assign pods to compute nodes. Moreover, each individual application can select a different scheduler to better fulfill its requirements. Without going into the technical details, Evolve has developed advanced placement and scheduling mechanisms for containers that automatically adjust their decisions depending on the runtime characteristics of the cluster. And this results in minimizing interference between applications to maximize the overall performance. Another important aspect of the execution environment is storage. So moving all applications into containers solves the issue of gluing together different and diverse parts of computation, but we also need to handle the storage aspect. It turns out that every different software component has different and sometimes conflicting assumptions about how data should be stored and accessed. For example, it's typical for HPC applications to require the presence of a shared file system with the same paths available to all instances of the application running in parallel. On the other hand, big data frameworks, which are mostly tailored for the cloud, use object stores like Amazon S3. To this end, we have implemented the unified storage layer for Kubernetes, which is an end-to-end solution that allows separation of storage configuration and workflow definition. So developers can write portable applications with configurable storage attachments selected on runtime, depending on the execution environment, the placement of data, or other parameters. The USL also allows transparent access to different storage solutions to allow workflows to benefit from many different current and future services. And also it helps in making workflows simple and easy to define, right? And this boosts productivity and makes the whole system more friendly. The unified storage layer is a step in the direction of handling storage heterogeneity in containerized environments, something that we expect to be of great importance for the convergence of HPC with big data. On top of the execution environment, we have the software frameworks, which are the runtime components for execution of workflows. These are packaged up in containers as microservices and are used for building blocks for workflow steps. Most of the microservices handle compute-intensive tasks like data ingest or extraction, data transformations, processing. They may use HPC kernels or other types of frameworks. And we also have incremental one-pass analytics over bounded data streams. So a workflow in Evolve uses multiple such services in different stages. Most commonly used ones are Kafka, Spark, and TensorFlow. We also support MPI by deploying on-demand virtual clusters, which are container-based HPC environments that allow MPI codes to run in Kubernetes using Slarm. And they include a wide range of libraries and compilers like CUDA, Gromax, and others. For all microservices, it is very important to consider how to exploit accelerators and the high-speed network and nodes to get the most out of the available hardware. In some cases, we also need to interface with the resource allocation extensions we discussed previously to achieve better container placement at Kubernetes nodes. At the front end, users begin their interaction with the Evolve platform through CarveDash, which is the Evolve dashboard. The dashboard provides a landing page for users, a web page interface where users can launch pre-configured services or applications. These deployments are based on configurable templates, so the users can also create their own in order to extend the available collection. For each service launched, the dashboard provides an external secure URL to connect to and make sure that the respective containers are run in separate namespaces for isolation between users. The dashboard also provides a simple interface to manage containers residing in a private image registry and offers an API for executing all the above actions through a notebook. So as shown in the figure, the first step of developing an application, the platform is going through the login process in the dashboard, which includes setting up your unified storage layer datasets and launching a notebook server and workflow controller. Then the user switches over to the notebook in order to write his workflows and launch them. We use Apache Zeppelin notebooks, which allow combining different languages in each notebook paragraph, or even customizing paragraphs with new languages and extensions. We also have implemented a custom Evolve interpreter for Zeppelin for simplifying the definition and deployment of workflows with Argo, which is our preferred workflow controller for Kubernetes. This custom interpreter is based on the Python interpreter and embeds a special library called Evolve, which allows programmatic handling of workflows alongside other management and data manipulation tasks through the same Zeppelin paragraphs. On the right here, we show an example of a simple single-stage workflow written in Python using the Evolve interpreter and library. At the front end, Evolve also supports high-performance visualization services that help analysts navigate big data repositories across multiple metadata dimensions. The goal is to render results of computational processes together with relevant knowledge, automatically extracted from public data in the form of digital content streams from news sites, social media platforms, etc. The picture on the figure on the right shows an example of the visualizations. The last component of the evolved platform is the vertical monitoring layer that is critical to both measure the performance and help end users exploit the system in an efficient way. We focus monitoring on 3 axes: processors, including node-level CPUs and accelerators, the software stacks with individual probes on different software middlewares used, and storage as it is critical to the performance of the workflows. We use standard open source tools like Prometheus and Grafana and make the results available via graphical interface or via API calls for other purposes like interfacing with the scheduling extensions discussed. This figure shows how all the components of the evolved hardware and software platform fit together and allow users to easily write portable code, which can then seamlessly be executed and scaled out on the available hardware. So the critical components again are notebooks, workflows, and containers. These are the basic building blocks that the users interact with, and they allow reproducibility and isolation between the users. So isolation is both from a security aspect and as a requirement to avoid conflicts between different software versions. Using these building blocks, code is easier to write and can potentially run both on HPC hardware when available, or move between HPC in the cloud or even different cloud providers. So to summarize, our experience building the software stack indicates that the convergence of HPC and big data is possible, but not easy, as HPC traditionally has its own, let's say, abstractions and uses specialized hardware, and it's not always feasible to bridge that with the big data paradigm. Big data frameworks, on the other hand, usually target commodity hardware and the cloud, and they do not readily take advantage of HPC hardware when present. So, however, we have shown that with the appropriate modifications, you can boost big data processing stages with accelerators and high-speed networking. So bring HPC, let's say, capabilities to the big data world. And by adding layers of abstraction over the hardware, we can run big data frameworks and HPC stages together as part of the same workflow. As I said, we expect this trend of containerizing different software frameworks to become the established way of running workflows in the following years, as containers allow decoupling from the execution environment and easily moving between installations and hardware-specific features. So this concludes the presentation. And I would also like to note that most of the software presented here, I think all of it basically is open source, and you can check our website, the Evolve website, for the details. Thank you very much.
So Evolve is about building an infrastructure for sure, but we need to validate this infrastructure. During the time of the project proposal, so almost 4 years ago, we have designed the platform with 7 different applications in mind. So there's some kind of co-design approach here, if you want. And this application, this pilot application, are here to validate the result of the platform, but they also need to be relevant and significant, both in terms of scientific results, industrial result, and also business needs. So we want to cover a large landscape of application in order to show the relevance of our platform. On 7 applications, they can be, roughly speaking, coalesced into 3 different baskets. So one is about satellite images. Obviously, here this is really the big data approach. We have a huge a massive volume of data to process, and this is typically application where AI is interestingly enough, these applications are using data provided by Europe by the satellite constellation Copernicus. The second set is about automotive industry. Here we have two different applications. Both are about predictive maintenance. One is based on numerical simulation on the comparison of a model and some sensor. And the second one is more like big data driven, where it's about analytics based on a large amount of record about the failure historic in kind of vehicle, brand, mark, and so on. The last basket is about transportation. So here we have an application from BMW. It's obviously an automotive manufacturer, but here the service that they're trying to build, that they are building actually, is more oriented toward public. So it's not individual public transportation, it's a ride-hailing application. And the other one is 100% public transportation. It's an operator in Italy, Tiemme. They operate a fleet of buses in Tuscany. And MEMEX is a consulting agency which is helping them in order to manage this brand new digital company. Just one slide per application. So this one, the first one, it belongs to the satellite images basket. Here it's from Thales Alenia Space, and they are performing change detection, which means that thanks to this Copernicus satellite constellation, every 5 days, the same area of Europe is recorded, photographed, and with this high-res resolution image, it's timestamp. And thanks to this, we can have a time series, a large database, where for the same location, we have a whole history of picture every 5 days. So using this, Thales Alenia Space, they are building a system which is going to automatically detect the changes which are appearing on the ground. So the purpose of this can be manifold. It could be monitoring the suburban extension, but it's kind of mid-term, and more short-term, it could be, for instance, to assess the damage by a specific weather episode on the agricultural growth of an area. For instance, they have a case with an episode of frost on the vineyard of Bordeaux. Here, what we have is a pipeline where images are fetched from the Copernicus data hub, they are calibrated, and then they are processed, and the machine learning algorithm is trying to detect the changes. Prior to the project beginning, it was something like 20 minutes in order to process one tile. Now, thanks to DAS being a parallelization with MPI but embedded within the Python library, this execution time has decreased significantly to 3 minutes. And now with Kafka, there is another level of coarse-grained parallelism. We can process multiple tiles at the same time, and in 6 minutes we can process 5 maps, which means that overall we have reduced the time by 3 and we have increased the throughput by 5. So it's a large improvement, and this has been done 100% on the Evolve platform. The second application I would like to mention is maritime surveillance. This use case is provided by Thales and is interesting by many aspects. One of them is the societal importance of the topic. It's about the security of the border of Europe, and specifically at sea and in the eastern part of Mediterranean. The second interesting aspect is more about the technologies that we have to deal with for this project, for this application. It's a question of data acquisition and fusion of data. So the first stream of data is coming from the satellite images, so the Copernicus satellite sending picture from this area of the Mediterranean. And the second stream of data is coming from the vessels themselves. By law, the boat has to send their location using a radio signal, which is an international standard, in order to inform the ground of where they are located. What we are doing in this application is that we want to cross-correlate the picture taken from the observation, for satellite observation, with the signal which is sent by the vessel. In case of mismatch, then obviously there is a notification which is sent to the operator. So it allows the operator to be much more efficient and do not have to track everything manually. But there is this information already provided by the system, by the application. And the second is to monitor if the trajectory of the vessel is unexpected. So if there is a steep turn, for instance, then again a notification is sent to the operator. Originally, this application, which is in production at Space Hellas, was a monolithic application, working well, but let's say that it was encountering some scalability issue. Then they did important software effort by breaking down the application in multiple pieces, in multiple software components, embedding every component into a container, and then orchestrating this container with a workflow. So now they have a modern application which is executed on the Evolve platform. On this workflow, deliver a significantly faster result. So the time to result basically has been decreased by a factor of 100. So the application is now 100 times faster than it used to be. We have a third application still operating on satellite. And here this is for agriculture optimization. So this use case that has been developed by Sibeltech. Here, from a technological standpoint, the main interest is that we are manipulating two different aspects of the platform. There is AI and there is numerical simulation. So the satellite images are processed through AI stage in order to identify the crop which is growing on some specific field. And once the crop has been identified, looking at the different picture provided by the satellite, we can observe their growth, and this growth is compared with a model of growth of the plant. And this growth model is implemented through a genetic algorithm, and it's massively parallelized using MPI, so we can compare what we are observing with what we are expecting. In case of a divergence, then there is a notification which can be sent to the customer, for example, to request more intrant or some ground inspection of the growth. And this application also is specifically IO bounded, and this is quite interesting as well. And it relies massively on open source code provided by ESA, plus, of course, the secret source from Sibeltech. Our next application is also about the comparison between what we observed and the model. So here it's not the opposite, but it's a very different topic. It's for engine. So the engine is instrumented with a lot of sensors, so we can have information about the number of rotations per minute, pressure within the cylinder, but we also have external information. Is the weather rainy, for instance? And all this information are recorded in a time series database, and we use this database in order to predict the behavior of the engine thanks to models that we are building actually with machine learning. And then if we observe a divergence between what the sensors are reporting on the model, so the future that we are predicting based on the past, then there is a strong hint that something is going wrong. And this misbehavior may be a hint about a future failure. So this way, we can implement predictive maintenance. This application also has been quite successful on Evolve. So not all the application has reached the same maturity on the platform, but this one from AVL and also specifically Thales Alenia space are very mature. And here we have a speed up of 50, factor of 50 in terms of time to result. So it's much faster, and furthermore, in terms of business, there is no degradation, so there is no extra burden push on the shoulder of the developer. The application remains big data. However, we have parallelization and we have faster results thanks to the HPC component of the platform. So here, this one, so I skipped the other automotive use case for the sake of speeding up a bit the presentation. So here, this public transportation also, the novelty, I mean, one of the topic of interest here, of course, there is the societal meaning of this, so it's providing, I would say, optimized on modern infrastructure for public transportation, which is key for the European citizen. And we have two interesting components in respect of the other application. First, there are this geographical location. So the visualization module is integrated within the workflow. And we have very advanced visualization modules thanks to the partner WebLizard technology. And the second aspect is that not only we can observe and assess the quality of the bus from the past, so we record everything and we compare with what we were scheduled on is there any kind of degradation of service. So we can assess the quality of service of the past, but also there is a real-time component in this use case. So it's possible to detect in almost real time if there is an issue somewhere in the bus traffic and to send a notification to the operator. So again, it's a way to optimize the business efficiency of the public transportation operator. Our application from the second public transportation application. So here this is a ride-hailing application. So what we want to do is basically to optimize a parallel version of a branch and bound algorithm in order to optimize the matching between the available car, a fleet of car in the street, and some customer appearing randomly on the map. So we are using a dataset coming from the New York City based on traffic and Uber traffic. And what we observe with this algorithm developed currently in-house by BMW is that we have some more very promising result and a good publication insight from this. At last, I would like to conclude these use cases by making a difference between what we call use cases of pilot application and proof of concept. So we have 7 applications. They have been here since the beginning of the project, so they are almost 4 years old. In this last 4 years, other technology has emerged, other need as well, as sadly we know with the COVID. And in Evolve, we have this notion of POC, which allow a specific application to be onboarded within the project, even if they were not initially registered in the project. So at the moment, we have more than 10 POC already active, some of them provided by other departments of Evolve partner, but some also from completely external organizations such as startups. It's still possible, there is still more room, so if you have an application that you would like to test on Evolve, please go to the ecosystem website, register, you will have access to the platform, you will have access to expertise, and we will learn from each other in a very cooperative way. We will validate our platform and you will get access to new technology, and also maybe it will be for you a way to get some R&D and confidence about future technology that you would like to buy for your organization in a second phase. At last, my very last slide is about the webinars. So the idea is that every Wednesday at the same time, 10:30 Paris time, we will have a webinar, a kind of dive-in. So it's not like this one, which was an introduction, an overview of the project, but we have session dedicated to some specific topic, data analytics, HPC plus Kubernetes. How do we orchestrate Slurm on Kubernetes? What do we do to accelerate the satellite imaging processing? All of this will be detailed during one session. So we have first 4 talks in June, and then a second string of session in October. So if you are interested by more of the technical detail of the project, please just register 30-45 minutes of technical talk with hands-on experience and screenshot and live discussion afterward. So I guess now it's time for me to thank you for your attention, and maybe we can also spend a bit of time to discuss the question which has been posed. Thanks again.
Okay, so I go ahead. So first of all, the questions is about what do you think about the convergence between the fabrics and the CPUs, for instance, the Bluefield technology from NVIDIA? This is a very nice question, and it gives me the opportunity to develop a little bit about all the trends, the works ongoing actually in order to extend the HPC architectures in order to on its path toward exascale, because in order to reach exascale levels of computing, we need to rethink completely and to rework, not completely, but a lot of parts of the HPC architectures in order to reach this level. And one of the trends is somehow to make the convergence between CPUs and the interconnection fabrics. And for this purpose, in fact, there is from my point of view, what I'm from my knowledge, there are different approaches to that. So you are on one hand, for example, the omnipath approach from Intel, which integrate the integration with their CPUs. Another approach, for example, from ATOS build also is something which is a little bit different by exporting some features from computing features from the CPUs to the network interface in order to perform some computing at the network interface in order to ease a little bit the workloads of the CPUs. And also, obviously, there is what we say in here about the DPUs, what I call the DPUs from NVIDIA, which originally is from Mellanox at the beginning, which is a little bit different due to the fact that it tries to relocate the computings at locally at different points of the networks and also storage, which is, how can I say, also go into the same way as other suggestions in terms of in-storage computing, stuff like that. That means that we perform the computings more closer to the place where the data is in terms of storage, in terms of network fabrics where the data is in movement. So there is a different approach, and obviously you're right. There is in the future there will be one of the combinations of those approaches in order to help to improve the computations, to reduce the workloads of CPUs, and to perform computations more closer to data. So the DPUs from NVIDIA is one of the, how can I say, potential, interesting potentialities for improving the performance of HPC. Hopefully that I have answered your questions.
Thanks a lot.
So another question we have in the chat is, could you elaborate about the metrics or features that have driven the choice for Zeppelin as the Evolve notebook? So that's a good question as well. I think initially we looked at several solutions. Zeppelin has a very tight integration with Spark and with Kubernetes, and it's easy to write paragraphs inside Zeppelin, and it will automatically launch Spark and deploy the executors in Kubernetes as containers, which was a nice feature. And it also allows us to mix and match paragraphs written in Spark with paragraphs written in Python and other languages. However, even as an option, we now have also Jupyter notebooks, and it's easy through the service templates that I mentioned to add other notebook servers, like I don't know, but we now support both Zeppelin and Jupyter.
Please don't miss our next webinars. As Jean-Thomas said in the beginning, they take place at the same, so every Wednesday at 10:30 CEST. So see you there. If there are no questions, I think we can wrap up. So thank you, and see you next time.
Thank you very much.
Thank you.